terms of it will sound like human voice that actually never happened.
Yeah, exactly. And so if you think about the generative adversarial networks that we're also going to talk about, but they make or they generate a sample based off of like a random sample, right? You randomly sample, but you potentially could also, that's one thing that you could also investigate, is you don't randomly sample, but you randomly sample plus you give it some context. And so I was thinking, like, what if I give it the context of like a word-to-vec representation of a certain word, or if I give it the context of a phoneme, if I just want to create like 1 out of 60 phonemes or something like that, right? And then, so maybe it then can create an actual phoneme sound.
Which will vary it will pretend to have different people.
Well, yeah.
Right, because this way you are only varying the input voice, but this way you're going around and you're creating aliens.
And so,
oh my God.
So the discriminator would also get this additional vector of like conditioning. So it would know, well, if you're not creating a sample that should look like a f or sh or something like that, then it should say, no, this is generated. It looks like speech, but it's not that speech, right? And so you theoretically could
the voice of
make
aliens.
like a concatenative speech synthesis.
Yeah, exactly.
Right? So you just make phonemes, and you like plunge them together.
Well, you can always claim that these are the voices of our ancestors that we lost, right? Because when you think about it statistically, there's more people there,
right?
And you're kind of there must be somebody that lived, but it's oh my God, it's fine. But can I ask you just what we can do? So we can not start from a random, but give it some sort of an outline within the space that we have. And then let it refine that outline.
So what you could do, I think, is like you could create a vector like this. And I'm not sure if you're able to get labels for all of this, but so the generator that gets like I don't know, like a normal distribution, 0 mean, 1 variance, and then so that vector can be like, I don't know, usually it's like 100-dimensional, but then you can add maybe like another 10 dimensions, and these 10 dimensions could be, for example, well, let's say it's only 4 dimensions, and then so it could be, for example, 1 bedroom, 2 bedroom, 3 bedroom, studio.
Right.
And then you could have like a 1 odd vector for each of them, and then you would know it has to generate a 1 bedroom or a 2 bedroom.
But we have to go and label 10,000.
Yes.
Yeah, that might hurt. That might hurt a little bit.
But
that would be interesting. I was thinking maybe more, instead of starting from a random sample, we already start with something that is that has some sort of an outline. Because that could be more, right? The first one, instead of being fed, it might not work.
But like you don't want to have too many dimensions. I mean, you could give it like the outer frame, right?
So that
and then
we need
fills
iteration.
in the middle part, or like the inside part. But I'm not sure. Like
we have to look into it.
Yeah.
We want to add one more thing, and that will be a simpler, because it's 3 of us and we want to shine as usual. We will try to do a labeled set that will look into floor plan and look into the images, 3D images that are photographs that are coming with it, and try to recognize based on that, because that seems to be more practical.
Yeah.
This is more on theoretical architectural side, and it does have applications in terms of architectural theory, but it's not something that is marketable or doable.
Yeah.
So
I would think into like look into like thinking, okay, what can I generate 1 bedroom, 2 bedrooms, etc.
that would be very interesting, except we have to, can we co-opt you guys to label? I actually have,
You could do
this-
MTurkers.
Yeah, I know.
Yeah.
No, I'll see if I can do it for free.
And
I have
we might.
13 students,
Okay.
and some ex-students from last semester, they will
Or
have
just
to
say
get-
like number of rooms, right? Yeah, and so if anybody else has like a study, sometimes at ICT we have some like maybe like $200-300 that we could like front or like an MTurk study or something like that. Maybe.
Because at the end, we generate a usable model that can be used some other time.
Yeah,
right?
like what we publish with it and stuff like that. Yeah. Okay, cool. Graphical models. So basically, graphical models are also referred to as like Bayesian networks, belief networks, or ballistic networks, and they're composed of nodes and arcs. So nodes are like represented with a circle, and arcs are like connections between circles. An arc cannot be like just going out of a node, it also has to connect to a node. And basically nodes are random variables and arcs are kind of like denoting their their relationship. So each node corresponds to a random variable, so this is kind of like the definition of it. So if we have a random variable x, we would have a node that's like a circle x. Then if we have a relationship between x and y, and we would know the type of relationship that we have. So like for example, if y is dependent on x, or like there's a direct influence of x to y, we would have a directed arc. So there's like an arrow going into the y. So and that basically represents the conditional probability of p of y given x. Okay. And another thing, we're only going to talk about acyclic graphs, and obviously, or also like directed acyclic graphs today. And obviously, like acyclic graphs are those that don't have cycles in it, right? Because there's no like relationship from x to y, from to z to x. Okay, so that doesn't exist. And yeah, basically the structure of the network is defined by arcs and nodes. So let's look at a couple of simple examples. So the most simple example I could come up with, basically I got it from the book, is two random variables. We have rain and wet grass. Okay, so we know that wet grass doesn't cause rain, right? Usually. However, like alternative facts might say different. But in our world, the fact-based world, rain sometimes causes wet grass. So when it rains, we like often have wet grass unless it's very hot and the rain goes away. Right, the water goes away very quickly. So basically, that can be expressed as a conditional probability in here, because we have this arc here that. The probability of having wet grass, given that it rained, is 0.9. So there's like a very strong relationship between the two. However, we can also have wet grass if it didn't rain, where it's 0.2. So what could have happened? The sprinkler, yes. So like you already know the example. But the other example could be dew, like in the morning or something, like whatever. And then we also are not in LA. Because the probability of rain is 0.4. So that basically, this model already allows us to express any relationship between those two variables. So we can completely express the relationship between or this joint distribution of p of rain and wet grass. And we only need these three variables. So one of the examples, for example, that we're going to get into is like, okay, so we could ask the question, what's the probability of wet grass? Or what's the probability that it rained given that we know that there is wet grass? Or what's the probability of rain that given that we see that there is no wet grass, and so on. So we can express this entire joint distribution, which can be expressed as this multiplication, because obviously there is a there's like, this is kind of like the root node, so that one doesn't have any other relationship, so like this was kind of like the root, and then this only has one relationship to wet grass, so we can express this joint distribution as P of R times P of wet grass given R, okay? And so only these three values can allow us to specify the entire joint distribution of this. So, for example, what is the probability of P of not R? 0.6, exactly. Because there is no relationship, we don't need to like infer something from wet grass. This is independent of it. And we know that P of R is 0.4, so that's 0.6 then, like 1 minus 0.4. What's the probability of P of not wet given R? Not wet given R, yes, 0.1. And the other one 0.8, okay? Because they are, so the important part here is that we don't need to like infer anything from the relationship with R, because we observe R in these as well, okay? So that's happening. Okay, so these are just the values. And you'll have all these examples on your slides. Okay, so next question that we could ask, which is a bit more interesting, is what is the probability, or like what's the individual marginal probability of P of wet grass? And so basically what we need to do in this case is, for this task, for wet grass, we do not observe R right now. So what we need to do is we need to compute the marginal probability over all the possible outcomes for R, okay? So P of wet grass equals like the sum over the expressions of R, which could be rain or no rain, and then of the joint probability of P and R, P of R and like rain and wet grass, and that can be expressed as basically these guys here. So we need to use this P of R, but then replace this R once with the normal R, and then plus the one where we say no rain, okay? And that basically then gives us the following probability, okay? So this is the marginal over R for the joint distribution, and we basically write this, and we have all of these guys, okay? We just yeah. So basically what this means is like, if we knew it rained, the probability of wet grass is 0.9, and if we knew it didn't rain, it is 0.2. But without knowing about the rain, the probability of wet grass is 0.48. Okay, that is dependent on the general probability of having rain and the relationship between observing rain or no rain and the probability of wet grass. Okay. So, and in general, this is kind of like a causal graph, and the cause of wet grass is rain, and we can also kind of like, and we can infer basically like what's the likelihood of wet grass, etc. Through this graph, but we also can turn this around, so we can observe something and then identify what could have caused this, okay? So basically, what we can what we can do here, for example, is we can observe that the grass is wet, but then try to identify what's the probability of that it rained. And we need to use Bayes' rule for that, because we can't just walk up this arrow here, okay? So we can't just turn that around, because this is a causal graph, like we have this fixed rule here. So basically the probability of rain given wet grass, so that's our kind of like the posterior, with the Bayes rule we need to turn it around, so probability of wet grass that it rained times the probability of rain divided by the probability of wet grass, which is the evidence for the observation that we have. And for that we have all of them, so we have the wet grass from just before, we have the probability of wet grass that it rained, which is this one, and we have the probability that it rained, okay? And then we just basically set that in and have 0.75, okay? And so like that's 0.9 times 0.4 divided by what we had before, which was 0.48, right? And I hope that that's correct. Okay. Before we move on and we kind of like create or make this network a bit more complex, we need to do some definitions, and like the more complex we get, we're gonna add like another variable here, or we add another variable down here, and so on. So like we're gonna make a third, we're gonna add a third variable to this network. So first, x and y are independent if p of x given p of x and y is equal to the probability of p of x, so p of x times p of y. And x and y are conditionally independent events given a third variable z if the following holds true. So if p of x and y given z is equal to p of x given z and p of y given z. Okay, so that you can already see like there is no connection between between x and y in this graph, and like it's a lot easier for us to kind of deal with graphs and visual representations than if we write all of this like these things. And then the other way to write this conditional independence between x and z, x and y, sorry, is p of x given y z is equal to p of x given z. Okay, so a couple of rules as well, like in graphical models usually not all nodes are connected to each other, so we don't want to have like these cyclical stuff. We only identify like a couple of causes for something. There are not too many relationships, so we don't want to have everything connected with like too many graphs. Like complex models can often be like broken down into smaller sub-problems, which we're going to deal with now. And local inferences for a small problem can then be propagated back into like a larger graph. We're going to come to this. And so we're going to talk about, I think, 3 canonical cases that are like sort of interesting, and where we can basically infer all of the other more complex cases from. Excuse me. So first of all, we have a serial graph, which basically means that there is a connection from x to y, from y to z. And x and z are independent given y. So if we observe y, there's no connection from x to z, and we don't have to walk that way. If we don't observe y and we want to, for example, infer x given z or something, we need to go through y, okay? But if we observe it, we don't have to do that. Because given z, like, and we observe y, we don't need to like move through here. We just take the y and add it to this, okay? just like to verbalize that, like say y tells z everything, and x does not add to the knowledge of z. So we write, for example, p of z given x, y is p of z given y. And we say y blocks the path from x to z, and the joint distribution can be written as follows. So we have 3 terms now, but you can see that only one variable is on these sides up behind the bar there. All right, so one example for this. We can observe that, or we observe a variable cloudy, there is rain, and then there is wet grass. So there's a causal relationship between cloudy weather, rain, and then rain has a causal relationship to wet grass. Okay, so we had that before, and now we just add this new node. And what we need to fully model this entire distribution down here are now 5 variables. So we need to know P of C, which is 0.4, rain given C, 0.8, and so on. Okay? So can we do stuff like probability for rain or probability for wet grass? And of course we can. So probability for rain is basically now calculated how. So we need to again, and before we had the wet grass, and then we had to calculate over the margin of like the rains because we don't observe that. And for rain now, we don't have to like go over a marginal for wet grass. We just have to go over the marginal for cloudy. So P of so probability for rain is equal to probability of cloudy times probability of rain given cloudy plus not cloudy times probability of not cloudy given rain. Yeah. And that can be computed as such. So we just use these variables here, and the cloudy and not cloudy. For wet grass, we again need to go only one step because there is no relationship between wet grass and rain. Wet grass and cloudy. So if we take the marginals over these of this variable, we don't need to go to the cloudy. So when we compute this, we can basically get to the following probability of wet grass. Okay, and this is slightly different from before because I think the variables changed a little bit. Okay, all right, and we needed the P of R for this calculation. Okay. All right. So another example. So when we observe that the weather is cloudy, what is the probability for wet grass? Okay. So P of W given cloudy. So we know about cloudy, and and we want to know the probability for wet grass. So basically, first we need to propagate the evidence through the intermediate node R, because like we observe cloudy, and that influences rain, and that influences wet grass. And so basically, what we need to do is compute over the marginals of rain for these this computation here. Okay. So this is how you utilize information that's up in this node down for the computation of like the likelihood for rain. Another example, and again we're using Bayes' rule here to propagate. So if we go forward, we can just compute it, but if we go backward, we need to use Bayes' rule to turn the issue around, so to say. And in this case, we want to know, given wet grass, what's the probability for cloudy weather. And so basically with the previously computed variables, we can do this. So first of all, we need to take this variable and with Bayes' rule we turn it around and divide it by this. So basically we get that variable. So we had P of C we know, 0.4. P of WC we just had that before, 0.76, and P of W we have 0.47. So we can easily compute that this is 0.65. So we can move backwards through multiple nodes in this as well. Again, using Bayes' rule. And the interesting part now is that knowing that the grass is wet increases the probability of cloudy weather from 0.4 to 0.65. So there is additional proof and additional evidence provided through these kind of positive relationships. So if you see that this relationship between the wet grass and the rain and the cloudiness are greater than 0.5, they are increasing the probability towards the end of something that's dependent on, or like that it influences. But if it were the other way around, if they were like smaller, right, then the probability that it gets cloudy goes down. So they're like, again, positive relationships, or like excitatory, so to say, in a neural network, relationships between variables, or inhibitory relationships. So that's kind of interesting to observe here as well. Okay. The next one that we're going to look at is the so-called tail-to-tail connection. But basically, we have one variable that influences or has a causal relationship to two other variables. So it's kind of like the parent of two other nodes. The joint density can be written as such. In this case, now we have x on both sides of those variables, and normally y and z are dependent through x, but if x is given, they're independent from each other. Okay. So this can be expressed as such. So basically, it can be this can be inferred through p of yz given x is basically xyz divided by x. That's this one. We can strike that out, so they're independent from each other. All right. And so we basically say, like, when the value of x is known, it blocks the path between x and y. And for general graphs, we'll see how to actually get these relationships with like a little example. Maybe not today, but there's like a tennis ball kind of rule that you can imagine to identify like which variables are dependent on each other in like general graphs. Okay, so in this case now we have cloudy influencing two variables, and if there's cloudy weather, we don't want to use the sprinkler, we want to save water, and if there's cloudy weather, it actually rains sometimes or mostly. So in this case we have an inhibitory kind of relationship between cloudy and sprinkler usage, and an excitatory relationship between cloudy and rainfall. Okay, and so we could ask, for example, the question. So, what is the probability of cloudy weather given that it rains? So, P of C given R. Okay, and so we have R given, and now what we want to do is basically we want to propagate this evidence back again towards the cloudy, and we can do this as such. So we set Bayes' rule, turn around, C, R, and then I compute these guys here. And what you can see is that in this formulation, in this function here, we do not use any of the sprinklers. We don't need to compute anything from here to get to that variable, okay? So given that it's cloudy, given that it rained, so given that it rained, inferring that it's cloudy, or diagnosing, or like using the observation that it rained to infer if it's cloudy or not, increases the probability of cloudy. So that's kind of this use that I mentioned for this excitatory relationship, where this probability now is larger than just the probability of the cloudy weather. Okay. All right. So what about the probability that it rained, given that the sprinkler is on? And it's interesting that we can kind of compute that. So probability that it rained, given that the sprinkler is on. So there's like, we have P of R given S, right? And the problem now is that we observe this here, but we want to get to that point. So we need to propagate through here and then down there. So we need to get the marginal over this guy first, okay? And basically, this is how you get at that. So P of R given S is over all the possible observations for cloudy weather, and this becomes a little bit more complicated because we can't really get those guys here directly. So we need to use Bayes' rule again, but that is correct. Okay, and then we can also compute P of R, so the probability that it rained. And basically the probability that it rained is the following, and is actually 0.45. And the interesting part here is that the probability that it rained, given that that we have the sprinkler on, is smaller than the general probability that it rains. And basically that kind of evidence that we have here is sort of explaining away, and it's removing support for this one because of the relationships that are noted in these probabilities here. In case that the sprinkler is off, so we know that the sprinkler is off and we want to know if it rained. Well, obviously we kind of turn this around, and in this case we won't have a value that's smaller than 0.45, but a value that's larger than 0.45. That's also like if you do some calculations in graphs like this, and you basically observe something, like in your calculations you see like a different trend, so you would for example see that the value for P of R given sprinkler is larger than a P of R, then you know that okay, there's something going on wrong, right? So you would know that you might have made a mistake somewhere. But anyways, this kind of this value here now becomes larger than this initial value. So this not sprinkler is supporting rain, while sprinkler is inhibiting rain. Okay. And then the third variable, is promise going to be the last one for today, is kind of like is the head-to-head relationship, where we have a node that has two separate parents, and the joint density can be written as such, where P of x, P of y, P of z given x and y. And x and y are independent and become dependent in this case when z is known. And we say that the path between x and y is blocked if z is not known. And when z or its descendants are known, x and y are not blocked or independent. So like you can have stuff that goes on down here, and if you observe something like there, in like a w variable, you have to propagate through those. Okay? And so in this case, we need to know these two probabilities separately. So P of sprinkler, P of rain, and then we need these variables here, basically indicating whenever one of the possible combinations is present. So the grass is wet in many cases, both when it rains or sprinkles, when it rains or not sprinkles, when it doesn't rain but sprinkles, but it's not wet when neither of them are on. Okay? And yeah, so we can, for example, compute the probability of wet grass, but now we need to compute the marginal across both variables, and we need to use all of those four guys here, and it basically breaks down to this. You can try that at home if you want to, but I don't know if this is getting much. Okay, so if we know that the sprinkler is on, we can check how this affects the probability. So for example, we know that the sprinkler is on, and now we want to know what if the grass is wet. So P of W given sprinkler, and now since the so we don't observe the wet grass, so we need to compute the marginal over the rain, and we get the following variable that P of W given S is 0.92, which is in this case larger than the P of just W that we just had calculated before. What about that the probability that the sprinkler is on given that the grass is wet? Well, so now we observe this, and we need to backpropagate this information to the sprinkler, but since we observe this variable now, we don't need to go through rain, and basically we can just use Bayes' rule to compute this. Okay? Alright. What happens if we do know that the grass is wet and that it rained? We can check how this affects the probability, and so basically of the probability of sprinkler, knowing that it's wet and it rained, now reduces the probability of, no, it actually increases it. That's interesting. That is funny. That's probably because of these high values here. Only minimally. Yeah, but it is smaller than the probability that the sprinkler is on given the grass is wet. So what we're doing basically is explaining away why the sprinkler, or like why the grass is wet, knowing that there is rain. Yeah, so we are explaining away, given that it rained, the probability of the sprinkler causing the wet grass increases. And obviously, like if we would do it the other way around, so probability of sprinkler given that it didn't rain but the grass is wet would obviously like give a boost over this one. Okay, and then you can try these guys at home if you want to, but I think we have discussed most of it already, and I'm getting tired. And so yeah, like just try these at home, and I think it might become more clear if you look at it in more like of a quiet hour, and then the next step would be to kind of combine the subgraphs that we had. So we first started off with rain and wet grass, then we had cloudy, sprinkler, and rain, and we had sprinkler, rain, and wet grass. And now we can combine this even further, so that we have, for example, this more complex graph where we need to observe a bunch more variables to fully model the joint distribution, and we can even compute now like relationships between observation of cloudy and given that it's wet grass, or like given that we observe cloudy weather, that what's the probability of having wet grass. And because this information propagates through two variables, we need to again like compute the marginal over 2, and it becomes quite complex at some point. So you don't necessarily want to do this all by hand all the time. Alright, but in general, Bayesian networks allow us to break down the inference into small groups, and that's actually where we're gonna go next time. And we can compute these inferences over like small groups of variables, and then propagate this information through an entire like more complex graph. And we can also use it to go backwards through observations and like infer like, okay, what could have caused this observation, so we can make diagnostic inference as well. And most importantly, these graphical models are kind of like nice and neat to visualize dependencies and independencies. Yeah, I think that's it for today. I think, yeah, it's just gonna be basically these. So these are the basics, and then you might be. Well, let's talk about them on Wednesday, like how we can use these basic rules in more complex graphs, and like basically what we're going to do is like break down the bigger graphs into smaller subgraphs, where these relationships between head-to-head and chain rules and tail-to-tail are kind of like present. Okay. Yeah, that's it for today. See you guys on Wednesday.